So I would like to add a few remarks about gradient descent. So it's about a common pitfall of gradient descent. Now, if we, for illustration, I'm going to use a few two-dimensional examples. So this is a function of two variables. So this is like z equals some function f of x, y, and these are level curves of this function. So the values are not indicated here, but they are decreasing towards the center. So at the center we have the minimum. So the way gradient descent works is as follows. So we begin at some point, let's say here, and then we make small steps in the direction of minus the gradient of the function. So it means that every step is going to be perpendicular to our level curves, right? So it's going to be something like this. So it's going to be perpendicular to level curves, 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 and so on. Well, actually, towards the minimum itself, the steps are going to become smaller because the magnitude of the gradient vector is decreasing. Now, if the our variables x and y are kind of on the common scale, then level curves look like circles or maybe like ellipses, but these ellipses have low eccentricity. So which means that the two semi-axes, so it's like two major semi-axes, the ratio is near 1. In that case, gradient descent converges very quickly, even with a large step. But let us look at a different example. Right? So now the features, they kind of they are on a different scale, and the problem is that what may happen is not that like one of these two features, if these x and y features, then is not like one of them is much larger than the other, but what we can have is they're kind of they're skewed. So level curves are ellipses, but they are elongated, so they have high eccentricity. So the ratio of the big semi-axis or the big axis and the small axis is high. So why this is really bad for gradient descent? Now imagine that we starting at some point here. Now if our steps are small, then what we will do is we make a small step here, then here we will get another ellipse, then perpendicular is this direction, so here we will get another ellipse perpendicular in this direction, and so on. So if the step in the gradient descent is small, then we still are going to converge towards the minimum. So this is not a problem. But what if you try to do a large step of the gradient descent? Specifically, if you stay here and you make a large step in the perpendicular direction, let's say here, right? So then the problem is that you sort of overshoot this next ellipse, the next level curve, and at this point you will do, if the step is large, you will make a step in this direction and you will overshoot again, and then you will overshoot again and overshoot again. So which means that if you choose a large step of the gradient descent, then eventually you will sort of reach the minimum, but you will do it in sort of unbalanced manner. So you will do you will converge towards the minimum, but you will have to wobble around a little, well, to the left and to the right. Now, what happens if we have an even worse situation, right? So if this really means that our level curves are ellipses that kind of a very, very, very high eccentricity, so very, very long and very, very narrow ellipses. Well, again, so imagine that we start here. So now, if the step of our gradient descent is large, then we will, you know, the first, sorry, the first step will move us from this point to this point. But then at this point, we kind of, so we have another level curve, and then we will move in the perpendicular direction backwards, and so on. So which means that we will have the same effect as in the previous picture, but only that effect is going to become even worse. So the longer and the narrower ellipses we have as our level curves, the more our gradient descent is prone to overshooting. So which means that in order for it to be nice and stable, we will have to choose a smaller learning rate. Now, if the learning rate is small, this is not really a problem, because what we'll have to do, so every time we'll make these little small steps, and then at some point we will reach this hollow, and then we will converge to the center. So this is a small learning rate alpha, but as opposed to a large learning rate alpha. So with a large learning rate alpha, we will do something like this. And what can happen is that um, with a large learning rate, the convergence may still be there, but it is going to be too smaller than the convergence with a small learning rate. But of course, if the learning rate is too small, then the convergence is going to be too slow. So which means that it is important to choose the correct value of the learning rate for the gradient descent, so that it doesn't wobble back and forth at the same time. So it is not too large, and at the same time it shouldn't be too small, because if it is too small, then it will just require too many steps to reach a reasonable approximation for the minimum.